Welcome to Playing with Junk. Before I start with the main feature, I want to show you something you probably haven't seen before. So that's a Dell R740 server. Looks like that. And this server has power supplies. And the power supplies look like that. So nothing special at the moment. They are normal 100 to 250 volt input and 1100 watts. But I also have these power supplies, which are also 1100 watts, but they have quite a different power connector. And they are used for DC input power, DC 48 volt. They say it's going from 48 to 60 volts, minus 60 volts, because common is here the plus pole and the negative pole is the power, so it's just a definition of which one is plus or minus. And I want to show you how that server works with batteries. And these are the batteries. It's 4 times 12 volt, 17 amp hours each, all connected in series. That's still 17 amp hours, but 48 volt in total. Let's connect that. So that's the IBM Z800 Mainframe. The Z800 is a cost-effective version of the Z900. I think that was the machine I took apart last time. It's not marked outside, but from the part numbers of the CPU I can see that must be a Z800. That's a whole family. There are different versions and models. I don't know which one is this, but well, maybe we find out a little bit later. Maybe not, but that's probably not so important. That's the back side of the machine. The large board here. There is the CPU. Here are mostly power supplies. There are a lot of power supplies in this machine. Also behind this cover here. And here are the power inlets, AC 230 volts, 2 times for redundancy. Let's plug them in. As I said, it has 2 power cords. And the connectors are quite a little bit exotic. I have never seen them before. They have a sleeve that pulls back to release the connector, and they snap in when connected. So let's do that. That's number 1. And that's number 2. Then we turn the main circuit breaker on, and we hear there are some fans starting. So let's turn it on. And of course we have also the support elements, these two notebooks here in the front. They are secured by this clamp here, so you can't open them before you flip that down. And you can't almost not open it with only one hand, and the notebook is working. It's currently in the BIOS setup. Let's press escape. That doesn't work. Because we have the wrong time. So the battery of the notebook, the CMOS battery, is probably empty. Yes, it's on 1988. Let's give it 2023. And we press F10 to save that. The other problem with the whole machine here is that both notebooks, by the way, here is the other one, are empty. Someone probably wiped the disk drives. There is no operating system here. And that means we can't turn on the big mainframe computer. And that's a pity. But if you want to know how it sounds when such a mainframe computer is turned on, you may watch my other video about the, I think that was the Z900, which I turned on, and you can enjoy the noise it makes. So, to make long story short, I will turn it off now, and then we'll take it apart. By the way, there is an interesting effect here on these AC input modules. So I can unplug the AC cable right now. You see, that's the sleeve that moves. This circuit breaker here turns off when I turn off the red switch on the front. They are both in the off position now. So every time you turn that emergency stop switch off, these two here circuit breakers will trip. Maybe they are remote controlled somehow. And every time you have to reset them when you want to turn on the machine. By the way, that's the power strip I'm using here. We have 32 amp connectors here, and then we have a circuit breaker and 16 amp connectors right here. That's a universal power strip that I built myself for all the racks and all the equipment we have to test here. We don't use all the connectors, but it's certainly good to have enough of them. Okay, we have already seen the two notebook computers here on the front. Of course, the whole door here can also be opened with the two computers, and it latches in. That's this lever here to close it again. Okay, and we have a lot of probably stainless steel, or maybe it's only zinc plated, I don't know. It looks a little bit like stainless, at least much of it. For example, this area here. Interestingly, everything is made in Japan. You know, good electronics comes from Japan. And according to the labels on the cables say it's made by Hitachi. So maybe the entire thing was made by Hitachi, or maybe only the fans and the cables, I don't know. And that's behind the big cover here. It's all power supply. We have 200 volt DC inputs. These come from a separate 200 volt DC power supply. That's something you see quite often, even in older machines. By the way, this machine is from 2002, so it's now 21 years old already. So we have a lot of indicators of diverse voltages, and we also have voltage regulators, so potentiometers. You can adjust voltages. That's something you don't see anymore in modern equipment. Everything is adjusted from a computer with software stuff. So we have a lot of more power going on here. I don't know what the output voltage of this is. By the way, I don't know much about this machine. So here we have a little schematic diagram, or a block diagram of all the modules. You can see that, and if you want, I mean, there are a lot of documents about this machine in the web. So even from IBM you get a lot of information about what all this means and what it is. By the way, even this label looks like it is printed in Japan. It's a typical font from Japanese labels and user manuals and stuff. It could as well be a Hitachi machine or a Fujitsu machine, so that always looks similar. Then here below the power supplies, we are still on the front side. There are I/O cards, a lot of them. I don't know if we have any Ethernet, maybe this one, fiber channel, fiber Ethernet, fiber channel is also possible. SCON, that's a special interface, a special bus for this mainframe computers. This is an SCON 2, that's FICON, fiber connector, fiber, yes, all special stuff. FLV, well, doesn't say a lot. There is, you can see the labels here for all the individual cards. The center card here with the thick black cables, they run through the machine to the front side where the CPU is. So that's the interface card that connects the whole block here to the rest of the system. That's the two black cables that come from the, I always have to look from the front side to the back side, and that's the CPU module here, the whole thing here. Then we have more power supplies. And of course there is room for even more, maybe also for a second CPU module. By the way, these connectors here that look like Ethernet, in fact they are Ethernet. For example, the two So they are just running around from one module to the other. But there are two cables, for example this here, that goes to the front to laptop number 1 or maybe number 2, and the other one for the other laptop. That's the Ethernet connection for this, and I think that's the whole communication between the laptops and the system to turn the system on and report all the things you must see on the front side. So there is another I/O cabinet here. You can see it's empty. It only has these empty covers here. And here we have token ring adapters for the laptops. They go into these card bus slots. And interestingly, they have a normal RJ45 connector here. And in this huge bulky adapter, that's IBM token ring. And I don't have the module where this go in, but you can imagine how large this connector is, and the module normally has about 8 or maybe 10 connectors, and that's then the size of an Ethernet switch, or in this case it's a token ring, whatever. I think it's not a switch because token ring is not switched, but yeah. Okay, and there are 2 more of these cards without any, well, adapter cables. So let's take one of these boards out. I want to show you something. So remember, this is only an empty shell. Okay, I got it out. And you can see it's also an empty canister in a other empty canister. Oops, yes. Yeah. What a work for nothing. And here you see the reason why this module sometimes stuck, because that's an EM shield. It's a fabric made of, I don't know, silver or nickel or chrome or whatever. It's elastic, it's flexible, it's self-adhesive, and if it's not moved for a couple of years, this surface here sticks to the next surface, which has exactly the same type of tape. So they are a little bit lighter. You see, this is also a tape strip here. And if they come together like that, they sometimes stick together. And to overcome that friction, it takes a little bit of effort. Okay, that's that. Let's just pull some random modules. I guess that's a ventilator, a fan unit. So let's see if that is right. It's like a drawer. Yes, that is certainly a fan. It's a big fan, and it's my fan. Okay, what is it? It has 45 watts. 0.6, yes, certainly. And it has 4 wires. And that's probably pretty interesting. We have 48 volt, we have ground, we have control, and we have a P sensor. Okay, I have a similar type of fan in my workshop. And I don't know if it's the same model as this one, but it has a very simple control, speed control. So you hook up the 48 volts. I think I had 24 volts, but I'm not sure. Ground, and then the control, you just need a potentiometer and give it a voltage between 0 and its operating voltage. And you can you can regulate the fan speed from 0 to 100% with no further electronic parts, just a potentiometer. I'm not sure if these are the same type, but I will definitively keep 1 or 2 of these things. And by the way, I'm pretty sure this is all stainless steel here. It's certainly not aluminum. It's certainly not, I don't know, anodized or nickel plated or anything. I think that is just blank stainless steel. And it's all screwed together except a few welding points here. Yeah, nothing is too expensive for these machines. Okay, let's see what's going on with these power supplies. Let's take one out. Maybe we get more information when it's out of the box. Okay, they are pretty short, but also pretty heavy. Let's have a look under the cover. All right, so we already have a little bit of clue what's going on. We have not 200 volt input, we have 360 volt DC input at 2.3 amps. That's about 700-800 watts. We also have some other voltages input, 24 volts, 0.2 amps. That's probably only to turn the whole power supply on. Then we have an output of 2.5 volt at 90 amps. Then 1.6 volt, 90 amps, 1.9 volt. Yeah, pretty unusual voltages and pretty high current, so I assume at least the low voltage here, that's for the CPU chip itself. That's the stuff normally on the PC is made on the main board by DC converters. Here you have removable DC converters. Okay, so it's pretty similar like the last power supply I took apart. There's also a video about 1 volt, I don't know, 100 amp power supply. So I guess these three are the 90 amp power supplies for 2.5, 1.6 and 1.9 volts. Then on the other side we have 3 other power supplies, or DC converters in this case, maybe for 5 volt, 3.3 volt and 1.2 volt, so with lower amps like 5 amps, 18 amps and 5 amps. That's probably a control board. Maybe there's a big chip on the other side. We can check that. Okay, I removed the screws and there is it. 3 chips, 3 times the same chip, as it looks like. Yeah, so probably control for the large DC converters. Yeah, probably yes, because these things have their own chip here, control chip. I don't know, maybe. It looks like so. What's that? That's a very small DC converter. It says power module. (2412), maybe from 24 volt to 12 volt or vice versa, for whatever reason. Also, a power supply needs a power supply to work, because yeah, there are chips, there are microprocessors, they all need their own power, and they need their power before everything else is working. Okay, there you have the LEDs, there you have the potentiometers, there you have some loose screws rattling around. Okay, a pretty nice design. And I know exactly what you are all yelling into your headsets right now. When does he take out the CPU? Well, I tell you, I'm going to take it out right now. So first, unplug the large and thick cables here. By the way, that's the connector. That's the other connector. And we have two screws, one on the top and one on the bottom. And because this CPU module isn't very heavy, it is quite a bit heavy, but not so much as the other. There is no fancy mechanism. It's just a simple slide out thing, and it weighs, well, maybe 7-8 kilos, and that's what's inside. Let's start with a look on this diagram here. That's pretty nice. That's the MCM, the multi-chip module. So that's the CPU, or multiple CPUs in one chip. That's probably, it's not written here, but I think it's the memory controller, because the next chip is the cryptography chip, it for data encryption, and the same on here, on this side here, memory controller and crypto 1 chip. And then we have memories, and a lot of memories. That's inside the module. Ta-da! So, let's have a look at this. Again, there is, I think, a lot of stainless steel. It's certainly, well, maybe the inner parts here, this feels like aluminium, but the outer shell here, that's not aluminium. It has a lot of rivets. It looks a little bit like an airplane. Yes, that's the air guide that guides the air through these fins here. Then we have memory, not so much. And we have one additional card that looks different from the memories. Is there a hint what this is? It's called KS-DIMM number 1. And it's the only KS-DIMM, whatever that means. We also see that the crypto chips have never been installed. In fact, there is still this Captain tape on it, this yellow protective tape. So these chips have never been installed. Okay, there is another space for chip, and that's most likely the memory controllers. By the way, it seems that Hitachi didn't make only the fans, they also made this board here. As you can see, Hitachi made in Japan. And yeah, they also made the CPU module board. I don't know who made the CPU chip. Maybe that's something IBM did. They have their own chip factories, but I think lots of these machines has been made in Japan and not by IBM. And that's one of the memory modules, one of the DIMMs. It's 1 gigabyte, so 1, 2, 3, 4, 5, 6, 7, 8 gigabytes for the entire machine. So keep in mind, this is from 2002. Well, even then for a mainframe that's not much, but I mean there's a lot of space for additional RAM. And well, I would like to know what this 1 gigabyte module cost in the day for this machine from IBM. Extra expensive. And all the empty slots are covered with this, well, slot covers, spacers, to prevent any dust to get into the connectors and, well, maybe to improve airflow. No, maybe not. That's not big enough for that. There are no levers on the side here, so these cards just come out like that. Another gigabyte or a gigabyte if you are a Back to the Future fan. And that's our KS DIMM. It's smaller. It's 256 megabyte times 12. I don't know what that means. It's certainly not 12 times 256. But maybe it's a 12-bit wide memory, and it's also clearly made, well, if it's not China, then it's Japan, and I think it's, well, of course Japan. It's the same stamp, the same font, the same, yeah. Sita. Okay, my hands are still dirty. Okay. That's another RAM module. So let's see how this CPU chip is attached. I hope it's only the 2 screws here. Maybe yes, maybe not. Number 1 and number 2. A little bit more. Yeah, so that's aluminium. Even if it looks like brass, it's aluminum. Okay. Yeah, I think there is more than only these 2 clamps. I think I get it. I have to... No. Okay. Let's try a little bit of brute force. Yes, it moves. Yeah, that's, okay, that's why it is so heavy. It has pins, millions of pins. Well, not millions, but certainly thousands of pins, like the old Pentium processors. And no, that pin is not bent, it's just a little bit longer and a little bit thicker than the others. It's a guide pin to guide the chip exactly into its socket. Okay, that's a pretty nice chip. Okay, focus please. And that's the socket. Oh, that's too close. Okay, focus. Oh, now it does it. Okay, so chip, socket, that's it. The base here, exactly this base here, is extremely heavy, so I think the whole thing is made of copper. You also see here these marks that look like, well, solder, and I think they actually soldered that. You can see here where the solder has risen a little bit between these fins here. So is it just soft solder or what is it? Yeah, it's pretty soft. Maybe a little bit harder than the usual electronic solder. No, maybe not much. Okay, probably the same. And I think lead-based solder and lead and tin. Okay, let's open these screws. Well, it seems even the chip has been made by Hitachi, which can be seen here. I hope you can see that. Yeah, I think so. And that's the reason why these screws are metric. I just tried an imperial Allen key and it didn't fit, so the metric are perfect. And yes, all that stuff that comes from Japan is metric since a very long time. They actually made the transition from the imperial sizes to metric. But I think the Americans will sooner or later get it and use it too. In fact, they do already, especially in the when it comes to mechanical stuff, but well, until this has reached the general public, I think in 100 years they still make races from 0 to 60 miles and not from 0 to 100 kilometers, but come on, at the end we all know how to convert that. Okay, so yes, it's getting loose. Will he break the chip or will he not break the chip? Okay, that's a piece of frame, very nice, very almost perfect surface finish. That's typical for Japanese products, at least in this category here. I still don't know what it is good for. Okay, ooh, that looks amazing. Oh, I know what they did. Wow, that's crazy. Okay, let's just look at that a little bit closer. They have this fins here, these heat sinks are glued to the individual chips. They are on this multi-chip module, that's the name. And then we have similar grooves here. And I think what they do is they made these grooves go into each other like that. So to make an absolute perfect or almost perfect thermal connection between the chips and that. So maybe it's not even glued here, but it's all only stuck with. Okay, let's try that. Oh yeah, it moves, it moves. Look at that. That's the most complicated heatsink design I ever seen. So we have a tiny heatsink that goes directly on the chip, and the tiny heatsink, where is the place, goes here and interfaces with the large heatsink through these slots. And there's, okay, and the spring here presses this tiny heatsink onto the chip. Yeah, that's it. Wow. That's a very interesting design. And also, I mean, the machine tolerances here must be quite good. Okay, and I also removed some of these capacitors here, so that's a problem with all these IBM chips. These capacitors break off extremely easy. I hope I won't break off any chip here. Let's clean it with plenty of isopropanol. Yeah, that dissolves it quite well. I think we won't see much of the chips because we are looking at the back side where the heat spreaders and the heatsink is connected to, and all the other features are looking down to the ceramic substrate, which contains all the wires and connections, and yeah. From another Z mainframe chip, I know that only the wires in this ceramic substrate underneath here are a couple of miles long, because there are so many lines, so many wires, or yeah, conductors, that this adds up to many miles of yeah, connectors, conductors, whatever. Okay, so everything is clean with isopropyl alcohol, a little bit of water and soap, and a lot of air to dry it off. By the way, if you leave isopropyl alcohol in a syringe, this happens. It will, the rubber here will shrink, or maybe the tube will expand, but however, it completely loses its airtightness. And of course, everything that was inside is now evaporated or leaked out. So if you use these one-way syringes for alcohol, always open them up after using and let it dry, and it will keep working. If the alcohol stays inside and has time to do whatever alcohol does with these rubber parts, this is the result. So that's not a good syringe anymore. Okay, I will also clean that mess, but I will do it a little bit later. One more thing about this chip. I will giving it away, and I will giving it to one of my viewers. And in fact, I will give it to the first viewer who deciphered my secret message, which I will show at the end of the video. So if you want that chip in your own collection, and maybe I give the heatsink too. It's a little bit heavy, but yeah, it's worth it to pay for the postage, even if it goes to the other side of the globe. Yeah, I give that away. And if you want it, you have to decipher the secret message. Okay, that's it for today. Thanks for watching.